Let us continue our discussion on transmission photoelasticity. I had mentioned that one of the key parameters that you need for comparing the results of photoelasticity with analytical or numerical methods is the material stress fringe value. And in the last class, we had seen how to evaluate this parameter as accurately as possible. We initially saw a single point method, which is a conventional approach to find out the material stress fringe value. And since we are in the digital era where computers are very well used for many applications, which you also find photoelasticity is not lagging behind, and people have tried to utilize the whole field information in finding out the parameters of interest. So, in that direction we had also developed a linear least squares approach, which collects data from the fringe field, utilizes information and then finds out the material stress fringe value as accurately as possible. We have also looked at the methodology is so well developed that the collection of data points should not influence the final result. So, you do a statistical conditioning, and I said for any of those procedures it is better that we go and utilize digital image processing techniques for extracting the data for you to analyze. What is the data that you require? You need the positional coordinates and the fringe order. So, you need to identify the fringe skeleton, and for finding out the fringe skeleton people only had techniques in the initial stages to mimic what we do manually. So, one of the earliest techniques in that direction was identify the fringe areas as binary information, black and white, and within the fringe identify the skeleton by removing the outer pixels progressively, and they essentially extended principles of optical character recognition to process the fringe pattern. And the whole process depends on what is the maximum thickness of the fringe in the field. You have to do scanning left to right, right to left, top to bottom, bottom to top, and this is essentially an iterative process. And at the end of the iterative process, though you get a skeleton, you are not guaranteed whether these skeletons merge with minimum intensity points, because in a broader fringe the answer may be slightly different. So, one way of circumventing this problem is to go and utilize the intensity information. Even while using the intensity information, people have developed mask based methods. We have not looked at them in the last class. We have only looked at a global fringe thinning algorithm. This is of a different approach, and what the focus is fringe skeletons that are continuous and free of noise, that is very important, that could be easily extracted by appropriately processing the results of fringe skeletons obtained by a finite number of scans. That is very important. There is no iteration involved, and in this case we use only 4 scans. I have 0 degree scan, 45 degree scan and 90 degree scan, and finally 135 degree scan. And if you really look at them, they are essentially orthogonal scans. I have a 0 degree scan and 90 degree scan, and what we found was when you do a 0 degree scan, it identifies fringe areas as well as gives you noise. And if you look at 90 degree scan, it identifies some fringe skeletons and also noise, but when I do a OR operation, I get complete fringe skeleton, but with some noise. And what we found fortunately was when you do the other orthogonal scans, 45 degree scan and 135 degree scan, and do the OR operation, you get the complete fringe skeleton with noise, but the noise what you get in this orthogonal set is different from what you get in this set. So, when I do the AND operation, we retain only the fringe skeleton and the noise is eliminated. This is the greatest advantage. So, the whole procedure can also be simply labeled as 90 or 0 and of 45 or 135. And if you want to get further details, you could look at in these references. These were essentially published in the 1990s, and the first paper deals with the essence of this algorithm. The second paper on comparative performance evaluation of various fringe thinning algorithms in photomechanics really brings out the advantage of global fringe thinning algorithm in comparison to other fringe thinning algorithms, both binary based and intensity based algorithms, which are essentially mask based. So, it is a step forward in the direction of finding out fringe skeleton comfortably as far as photoelastic images are concerned. Photoelastic images have very high contrast, and it makes identification of fringe areas very simple, and use the minimum intensity position to extract the skeleton. And I also mentioned in a complex fringe pattern like what you have in a crack tip isochromatics, instead of doing the scan orthogonal to the fringe area, I said 4 scans globally can identify the curvature also. Even with different curvatures of the fringe, the skeleton could be extracted, and here you do intelligently utilize the logical operators and you extract the fringe skeleton. And the next topic what is important is we have n f sigma by h equal to sigma 1 minus sigma 2. We have seen how to get f sigma. Now, we have to find out how to label the fringes. It is a very crucial aspect. If you look at photoelasticity, the arithmetic involved is very, very simple. For you to find out the stresses, the arithmetic is simple, but for you to get the stresses, you need f sigma and you need fringe order. And now, we take up how to label the fringes. See, one of the important aspects in any of the optical techniques is to find out how to label the fringe orders. And in photoelasticity, you can get assistance in labeling the fringe ordering by looking at properties of isochromatic fringe field, properties of isoclinic fringe field, and also invoking certain principles from mechanics of solids. See, what is important is with modern developments, you have the advantage of computer based methods which provide you fringe order at every point in the model domain. Though they are automated methods, my recommendation is it is better from learning point of view, you should also know how to look at the fringe pattern and label the fringes. This knowledge would complement your further learning. And we have seen in the case of photoelasticity, you have many important fringe field features such as source, sink, saddle point, singular point and isotropic point. And also mention that source, sink and saddle correspond to properties of isochromatic fringe field, singular and isotropic points correspond to isoclinic fringe field. And it is to be noted that there is no standard procedure to order the fringes. These are only guidelines, and it is better that you look at the problem, approach in one fashion and order the fringes, verify this by another approach. So, I am really giving you more than one method to arrive at the fringe order. And what we will do is, we will look at the problem of ring under diametral compression. I had already mentioned that fringe ordering in a ring under diametral compression is really complex. And what is shown here is, I have a conventional loading arrangement of a lever arm loading, and in this the load is changed. So, essentially what you have is the load is increased and fringes form and then move out. And what I have here is I have the inner surface of the ring is a free surface as well as outer ring except the load application points, it is a free surface. And what you find here, the fringe field is very complex. Do not carry the impression you had seen the problem of disk under diameter compression, where you had the outer boundary except the load application point, fringe order was 0. So, you should not conclude that any free boundary you will have fringe order 0, it is not so. It was a very special problem, even theory of elasticity solution said that outer boundary the fringe order is 0. Here I have a ring under diameter compression, I look at the outer boundary and inner boundary, I have several fringes which touch the outer boundary as well as the inner boundary. So, you have to find out the fringe order very carefully. And we had seen in the last class a particular feature, what happens in these type of zones. We have looked at that fringe vanishes at this point. As the load is increased, fringes appear and they vanish at this point. And I said akin to your fluid mechanics, you could call these points as sinks. So, from this knowledge what do you get? What is the fringe order at the sink? One common mistake people will do is sink is 0. It is not 0. It is only at a fringe order lower than the neighborhood, because what you find is as the load is increased, the fringes develop and they go and vanish at the sink. So, this is what you are really looking at. And the other feature what we have looked at is we have points where fringes originate. I have the fringe originate here, I have fringe originate here, I have the load application point and they move out. And I also caution that you have a fringe vanishes here and you have another situation where this fringe does not vanish, it remains in its place, and as the load is increased, the density in its neighborhood increases. And I had also mentioned that such a fringe is essentially a zeroth fringe order, it does not move as a function of the load application. And we would find out this identification of zeroth fringe order by other methods also. If I take a color image of the fringe pattern using white light as a source, then a black spot in a circular polariscope will definitely say it is zeroth fringe order. If you have white light source, if I am able to look at it, it is well and good. But if you do not have, you should also have methodologies to identify what is the zeroth fringe order. But in this case, even if I know the zeroth fringe order, if I do not know how the gradient is along this direction, there is no way I can label the fringes. Understand how complex this fringe field is. So, what we will see is we will look at the definition of the sink, that is what we had seen first, and you have a sink here, you have a sink at the bottom also. A sink represents a point at which fringes vanish. And how do you get this? Only when you gradually increase the load, you would be able to identify whether it is a source, sink or a saddle point. These are all functions of fringe formation as the load is increased. Otherwise, by giving a static picture, you would not be able to identify unless your eye is tuned. Here there could be a possibility of a sink, possibility of a source, possibility of a saddle point. You would not be able to quickly say that this is so. So, if you want to reconfirm this, gradually increase the load and decrease the load and find out whether it is a sink or source or a 0th fringe order, that you will have to find out very carefully. And what you will have to keep in mind is, sink only says it is at a lower fringe order compared to the neighborhood, but not necessarily 0. If the load is such, you may have a 0th fringe order. There is no bar that sink should not be a 0th fringe order. It depends on the particular load that is applied. It is at a lower fringe order. And we have also looked at what is a source. Source, by definition, you have the load application points, you have the stress concentration zones, and the tips of cracks or stress risers, and they act like a source. So, what happens is, when you increase the load, the fringes start to appear from this source and move out as the load is increased. So, these are the fringes that come first when load is applied. As the load is increased, fringes originate, and if you label a fringe order, and the fringe order moves with the fringe as the load is increased. And you have many such sources in the case of ring under diametrical compression, and you can also locate the sources. I have not located all of them. This gives you an indication how to go about in locating the sources. And this is the key point. As the load is increased, fringe orders appear at source and propagate to other areas. So, if I label the fringe, I can trace its label as it moves out. And finally, you have another fringe feature which you could identify in isochromatic fringe field. It is a saddle point that comes directly from how does a saddle is. In a saddle, you have on one direction the curvature is like this. So, the fringe order should increase on either side, on other side fringe order should decrease. So, you sit in a saddle, horse saddle, similarly you have a saddle point. With this definition, can you recall, is there anything special about circular disc under diametrical compression? We had looked at circular disc, the fringe pattern was very simple, it is very academic. You had only the minimum number of fringe loops. It is easy for you, once you identify 0, you have a point where load is applied, the fringe order is increasing, and labeling was so simple 0, 1, 2, 3. You would see that was simple only when you compare it with ring under diametrical compression. If you do not see ring under diametrical compression, you would not be able to appreciate that. And we have actually used circular disc to find out the material stress fringe value. We also found out what is the fringe order at the center of the circular disc. What happens in the center? If you go diametrically up, I have load application point. So, fringe orders increase on either direction. So, it is like, I have this base, fringe order is increasing like this on one direction, fringe order is increasing on the other direction. On the horizontal diameter, you have a situation, fringe order, this is the base, fringe order decreases, fringe order decreases. So, center of the circular disc is a saddle point, fine. And in that case, I could find out this as two orthogonal lines. It is not necessary, it is always orthogonal. So, we will see what is a saddle point. Having looked at circular disc, center is a saddle point. A saddle point is bounded by two families of isochromatic fringes. So, in one direction you will have fringes increasing, in another direction fringes will be decreasing. So, it essentially gives you the gradient information. So, I should identify saddle points in the field, and this is more to check. Suppose I have ordered the 0th fringe order, and then I am moving from 0th fringe order and I label it. If I identify a saddle point and if we counter check from the saddle point, what I do, both should match. If it is not matching, then you will have to go back and find out what mistake you have done. So, it acts more from a verification point of view. And what you have here is we will also look at some of these aspects. What I will do is I locate the saddle point and then magnify this picture and then look at the feature. So, what I have here is the fringes merge like this. So, you have this kind of a feature. So, wherever you have this feature, you have a saddle point located. I have another feature here, saddle point is located, and this is a source, and this is also like a source. If you look at a line like this, fringe is increasing. If you look at a line like this, fringe is increasing, and if you look at a line like this, fringe is decreasing, and similarly fringe is decreasing in this direction. So, it is like a curve here, it is not like a perpendicular lines like what you see in a circular disc. So, you can quickly appreciate that wherever the fringe appears like two branches, they merge and go, all those points are behaving like a saddle point. So, how many saddle points I have now? I have 2, 4, 6, 8, 10 and 12 saddle points we have identified in a ring under diametral compression. And this is more like verifying how to check the ordering of fringes, because saddle point we know in one direction the fringe should increase, in another direction fringe should decrease. So, whether this feature is captured is what you will have to look at. And all along we have not bothered about what is the sign of the boundary stresses. We have looked at beam under bending, we have looked at ring under diametral compression. How do you identify whether the sign changes? We will have a methodology to find out separately. We can also look at from a fringe feature. Suppose I have a 0th fringe order on the boundary. How can you pass through 0? When I pass through 0, I need to have sign change. So, we will also identify certain points on the outer boundary as well as certain points on the inner boundary where the fringe order is 0. I would be able to do that if I look at the isoclinic fringe field. On the other hand, in the case of a circular disc, you had the entire outer boundary was 0th fringe order. Here you are not having the entire outer boundary as 0th fringe order, you will only find out just 4 points. I have point 1 here, point 2, point 3 and point 4. If you look at very carefully, as the load is increased, this fringe order remains as such. If your eye is tuned, that is the reason why I keep this animation for such a long duration, you find this is getting compressed into this, that is, it is becoming sharper and sharper, you still have a fringe. So, any fringe that does not change as a function of the load is a 0th fringe order. And a similar fashion you also have 0th fringe order on the inner boundary. It is difficult to observe. If you look at here, as the load is increased, the density of the fringes increases, and this is again a 0th fringe order. We will verify this by a property of the isoclinic fringe field. And what you find here is, I have 4 points in an inner boundary, 1, 2, 3, 4 and 4 points on the outer boundary, 1, 2, 3, 4, where the fringe order is 0, and fringe order is also 0 at these 2 points. Whenever I cross the fringe order 0, the sign of the boundary stresses changes on the boundary. You have to understand that. When I cross 0, I can cross only when there is a sign change, and you have 2 sinks in the ring under diametral compression. So, now what we look at is, we look at what are all the properties of the isoclinic fringe field. And here again I have a nice animation. For a fixed load, you have the polarizers which are kept crossed or rotated. And what I want you to see is, look at the animation, observe. In this class there is more of observation and less of notes taking. You have to appreciate how the whole fringes appear, and there are many features you find, what is happening at this point and what is happening at this point. Very interesting, there something is happening. What is happening to this branch of isoclinic? The isoclinic actually rotates in an anticlockwise direction. I have all the isoclinics pass through the point. Do not you find that? Because here I am continuously rotating the polarizer analyzer combination crossed, and what you find is you always have an isoclinic passing through this point of interest, and you also find the 4 points which I said in the outer boundary, here also all the isoclinic pass through the point of interest. And many things you can understand, this is happening in a particular fashion, the way as the polarized analyzer combination is rotated, here all isoclinics pass through, but it moves in a particularly different fashion than what you find in this. Here it is anticlockwise, here it is clockwise. Okay. And similarly, even if you look at the points which are on the inner boundary, can you see this point? This point was difficult to locate in a isochromatic fringe field, and here I have one point where all isoclinics pass through. Do you see that? This is the observation I want you to make, and this is possible in an animation like this. It is difficult to do it in a actual laboratory class unless you very intently see this. Can you see this point? I have the cursor located at this point. You find all isoclinics pass through this. When I rotate the polarized analyzer combination, suppose I take a point like here, one isoclinic comes and goes, that is all. A particular isoclinic comes and goes at this point. On the other hand, you always have isoclinic at this point. So, this itself gives you an indication how to identify the zeroth fringe order. You have an appreciation of that, we will see that in detail. So, to aid your visualization, I have also plotted the isoclinics in steps of 10 degrees, and this summarizes some of the observations. We will see those observations, and what I find here, at this point all isoclinics pass through, at this point all isoclinic pass through, and at this point you have all isoclinic pass through. Likewise, you see, but I also have another 2 points where the isoclinic originate. Suppose you look at the load application points, they also all isoclinics merge. So, you have made these observations. First you make the observations, then we find out and classify what are all the different fringe features. And this animation also shows that I have the polarizer and analyzer cross and they are rotated. That is how you are seeing these isoclinics moving through the fringe field. Now, what we will do is, we will go and see what is an isotropic point. An isotropic point is one through which all isoclinic pass through. You have already seen, I have already helped you to tune your eyes to see that there are points in the model domain where all isoclinics pass through. Since you have seen that, now you can appreciate this point, and you have the advantage fringe order at an isotropic point is 0. See here, I tried to find out property of an isochromatic fringe field by looking at isoclinic fringe field, I can verify, I can switch back and forth and then verify this is zeroth fringe order. There is also a methodology to verify it as zeroth fringe order even in a circular polariscope, but if you have a confusion you can always verify it, you always need some verification. So, what we find here is isotropic point is one through which all isoclinic pass through, and whenever you have a rule there will be an exception. The load application points are not to be considered as isotropic points. And why do you call this as an isotropic point? It is termed as isotropic because at these points the loaded polymer does not behave like a crystal, but behaves like an optically isotropic material. Every axis is principal stress direction. You have, even when you do the principal stress direction evaluation, you can have a situation every direction is a principal stress direction, that is what is happening in an isotropic point. So, you have several isotropic points located. The isotropic points are also now marked in the fringe field and you can have a look at it. So, what I have here? I have 4 of them, 1, 2, 3, 4 on the outer boundary. I have 4 of them in the inner boundary, 1, 2, 3, 4 and 2 in the horizontal diameter of the ring. So, you have only at these points fringe order is 0. Look at here, the complexity is manifold in a ring under diametrical compression. Yes?
The other one in this under diametrical conduction.
Yes.
Do we have this isotropic point?
You do not have an isotropic point.
But we do have zeroth fringe order.
That is not the intention there. See, the definition of an isotropic point is where all the isoclinic pass through. And in fact, I had given you this as a home exercise where the circular disc is so special. I said the isoclinic will meet the boundary at what angle. So, each point on the boundary you will have one fixed isoclinic meeting, whereas in an isotropic point all isoclinic pass through. Do not carry the information that zeroth fringe order means all isoclinic pass through. No, the contrary is not true. When all isoclinic pass through, fringe order is 0. You take that statement, do not look at the other statement. I take the beam under bending, I have a zeroth fringe order at the horizontal. You have only one isoclinic, there is no other isoclinic, because the isoclinic is horizontal in the case of a beam. Zeroth isoclinic only pass through it. So, if you want to find out the zeroth fringe order, take the cue that if all isoclinic pass through, that point is zeroth fringe order. Do not use this for zeroth fringe order. Do not look for more isoclinic to pass through in every zeroth fringe order. There are special situations. The special situations are what you see in a beam under bending and disc under diametrical compression. These are exceptions. You should not mix up exception with a general rule. It is good that you asked that question. It is a very valid confusion that you can come across. And so, I have 10 isotropic points have been identified, and we also sub classify. What you look at here is when I have an isotropic point lying on the boundary, I will label it by another name. I will call it as a singular point. So, what we say is an isotropic point lying on the free surface is termed as a singular point. So, what happens in a singular point? We not only have fringe order 0, but stress tensor is also 0. Why it is 0? Because it is a free surface, there is no stress acting perpendicular to the direction, it can only be tangential, and you do not have anything perpendicular, that is 0. When fringe order is 0, it only implies sigma 1 equal to sigma 2. The students will have a confusion when I say 0th fringe order, everything is 0. This is one wrong conclusion you can think of. it only implies sigma 1 equal to sigma 2. Suppose I have a zeroth fringe order on a free boundary, stress tensor is also 0, and that is indicated by a singular point. And if I locate the singular point, you yourself know there are 8 such singular points in the ring under diametric compression. So, now you have a fairly good idea what is a source, what is a sink, what is a saddle point, and what is a isotropic point, and what is a singular point. And we have also made one small distinction, that when you look at the isotropic points, you find that the isoclinic fringes move in a particular fashion. We will see what it is. There is a special distinction. You also classify them as isotropic points are positive and negative, depending on the way the isoclinics rotate when the cross polarizers are rotated. And that is what you had seen very carefully. There is a particular aspect happens at this point. When I rotate, they rotate in the same fashion as the polarizer analyzer combination, and you have a simple labeling. You call this as a positive isotropic point, and I will call the other one as negative isotropic point. I just classify, I only want to record my observation that in one case when I rotate the polarizer analyzer combination, the isoclinics also change in the same fashion in the point of interest. There is a synchronization between the way I rotate and the way you see the labeling of isoclinics. You have that as positive isotropic point, and you have to have what is the ultimate use of it. See, all this is to verify your labeling of fringes. I can label the isochromatic fringes, I can also label the isoclinic fringes. In isoclinic fringes, you have to plot them separately and then do it. You can't take a photograph, you have to take multiple photographs, extract isoclinic and separately prepare a composite image, and in the process you may make an error. And what you find here is, I can zoom it and then show. See, if you look at, I have a point here, I have another isotropic point here, I have another isotropic point here. You have something interesting happening. When I move from this isotropic point to another isotropic point, in between the sign changes. That is how it will appear. So, this is a nice cue for you to verify whether you have labeled the isoclinics correctly. And it is very interesting to know, it is better to know some of these aspects. So, I will always have this isotropic points in a combination. We have seen what is the positive isotropic point, we also see what is the negative isotropic point. This is rotating anti-clockwise and this is rotating clockwise, and I rotate the polarized analyzer combination in an anti-clockwise fashion. So, when that sense and this sense matches, I call that as a positive isotropic point, I call the other one as a negative isotropic point. Are there any questions at this stage? Fringe ordering is the most complex, and we would see further what are all the other aspects of solid mechanics that I can employ. Now, you have seen the fringe field, they are very rich animations, and I am sure you would have got a gist of what these fringe orders are. And this is what I have said, that in most problems identification of zeros fringe order is possible based on the mechanics of the problem. See, if I have the zeroth fringe order and if I know the gradient information, it is possible for me to label the fringes. and I can get the gradient information by looking at a color code. And once I mention 0th fringe order, let us also look the exceptions, because that was also discussed briefly when we looked at properties of isochromatic and isochronic fringe fields. So, in the problem of a beam under pure bending, the neutral axis is a 0th line. It is not just a point, you have a complete line which is a 0th fringe order, and because of this luxury of the multimedia, you can quickly see what is happening in a beam under bending. And what I have here, I have this 0th fringe order at the center. While we looked at beam under bending, we never bothered to look at as the load is increased, this remains stationary. Now, you have seen this amply clear for the case of a ring under diametrical compression. Now, I increase the load, the density increases in this zone, whereas fringe order 1 has moved, fringe order 2 has appeared, but fringe order 0 does not move. This is a very important observation. And another question we have not raised all along, I said you have fringe orders only as positive integers in photoelasticity. Neither you asked me how to find out whether it is a tension side or compression side by looking at the fringe order alone. We will see a methodology experimentally, but because it is a simple problem, if you know how you have applied the load, we have applied the load like this, it is bent like this. So, the top fiber is compression, bottom fiber is tension, that we know, but in general you have to do auxiliary methods to find out the sign of the boundary stress, because as such fringe order has no negative sign, fractional fringe order has, not the total fringe order. Total fringe order you may say 1.23, 1.24, you will always attach a sign as positive, because sigma 1 minus sigma 2 is always positive. So, this also we need to learn as part of fringe ordering, as part of understanding what is the stress analysis information, we also need to know whether it is tension or compression. We will postpone that discussion for the time being. And what have we seen in the other case? We also looked at circular disc under diametrical compression. It is again a special case, except the load application points, you have the outer boundary as 0th fringe order. That is again a special case. Do not confuse the special case with a general rule. So, these turned out to be very simple problems for fringe ordering, very simple. Beam under bending and circular disc are the simplest problems you can think of, where I have multiple fringes and I can also label them one after another comfortably. So, I have this as 0, 1, 2, 3 and so on, and this is your saddle point, because fringes increase in this direction, fringes increase in this direction, fringes decrease in this direction and fringes decrease in this direction. So, this is also like a indirect check. And you know, we have seen as part of your assignment, I have asked you to find out what happens in free external corners, and you had seen mathematically from the definition of stress vector, and also you have identified stress tensor has to be 0 on free outward corners, and this is a very useful information in complex problems. See, I am also taking you from simpler fringe fields to more and more complex fringe fields. In fact, I am going to show you a load cell 2-dimensional model, where you have taken the fringes with white light. Even with white light, the fringes are very complex. I said if you use white light you have rich colors and it is easy to label the fringes, even there the fringe field is complex. We will see that. I have this here and I have this fringe field, and this is used in many popular load cell design. This is a spring element and they would have strain gauges put inside this boundary of the hole, and this also can be hermetically sealed. And what I have here is this is subject to the compression along this direction and this direction, that is what you see here, and there is no load applied here. So, I have a free external corner, I have a free external corner, I have a free external corner, and look at carefully in all these free external corners I have the fringe as black, and you see a black line here. So, this is again a zeroth fringe order, this is again a zeroth fringe order here, and in between you see a point where there is zeroth fringe order. So, this gives you an indication, it is not that zeroth fringe order you have a line all along the model or line all along the boundary like in a circular disc. You may have pockets, certain points are 0, you may also have some line, some points. So, fringe ordering becomes extremely complex, and I have a nice color code, and all know if I have a blue red transition, what is the fringe order here? What is the fringe order here? This is fringe order 1. I have 0, I have 1. I have 0, I have 1, because this is a source. So, fringe order increase in this direction, and if you look at here, the fringe order also increases in the direction. So, this is how you find out, and you find out how to label the fringes. And let me ask one more question. See, you had also seen long time back fringe order in the case of a plate with a crack. You had seen color fringes. You go back and see your notes, where was the zeroth fringe order? I have a tension strip, I have a crack, and I have loaded it, because when you learn some of these concepts, you only see what you want to see. I have not asked you to certain features in those classes. I had only focused that when I have a plate with a circular hole, when I have a plate with an elliptical hole, when I have a plate with a crack, the fringe density will be very high at the tip of the crack, that was emphasized. But we have not looked at numbering the fringes. Now, we are having a discussion on numbering the fringes. Go and look at your fringe pattern and find out what should be the zeroth fringe order. Take this as a home exercise, and then label the fringes in the case of crack. In the case of a crack problem, if you know 0, you know the stress concentration point. So, it is easy to label the fringes, you do not need anything beyond that. But on the other hand, if I have to go and identify the fringe order in the case of a plate with a hole, it is little tricky. Plate with a crack is simpler to label the fringes. Plate with a hole, it has certain features common with ring under diametric compression. So, this is the way you will have to go about. So, in this class what we had looked at was, we had reviewed what is the advantage of using intensity information in identifying the fringe skeleton, how the methodology becomes very simple and computationally efficient in the beginning, and you need to find out f sigma. So, we have looked at f sigma, a methodology to utilize the field information, and we also looked at a digital technique which provides you the field information. Then we moved on to finding out the fringe order. We looked at the isochromatic fringe field, we looked at the isoclinic fringe field, and we saw certain aspects of isochromatic fringe field can be understood by looking at the isoclinic fringe field. And later we also developed what concepts of solid mechanics you can utilize to identify the zeroth fringe order. If I have the zeroth fringe order and if I also know the gradient, it is easy for me to label the fringes, and once I label the fringes, as a verification you can utilize the properties of isochromatic fringe field, properties of isochromatic fringe field to double check whether your labeling is indeed correct. Though this may look redundant in these days where you have software to provide you information, like I said, both in finite element technique and in experimental methods, computers should be used to assist you. You should not blindly believe what the algorithm says, because if you have done wrong boundary conditions or wrong interpretation of your experimental results, you can go wrong. You should know how to do and verify the results. So, the methodology of fringe ordering will help you to verify even your result from a automated software that provides you fringe order.